So I'll be presenting this work that we did at Columbia, and as you might have guessed, I'll be talking about texture synthesis, and more specifically example-based texture synthesis, where we're given as input a simple example image or exemplar, and we seek to generate outputs having similar characteristics or features. Now,
Hi,
as you've heard, this sort of
I'm the technical papers.
this sort of research has been around since around 1995, so we've gotten fairly good at synthesizing images such as this one, which has a similar appearance everywhere in space and also a fixed feature size. However, there are a class of textures that have not been as well studied so far in this context. As an example of one of these, I'll show you this texture here. And when we view it at this resolution, we see grassy and rocky features, and so far this looks like something we could generate using an existing method. However, if we zoom out a bit, we see that in fact this is part of a larger texture, and we have other features present as well, like mountains and lakes and fields. And the thing to notice here is that these features exist at a larger physical scale than the ones that we just saw. And in fact, we can keep zooming out and see that we have features even on the scale of continents and oceans. And it's this presence of features at a wide range of physical scales that characterizes the type of textures that we're interested in today, or in this talk, and we term these multiscale textures. Now, an interesting and a natural question to ask now is, how do we synthesize a multiscale texture? Or can we even do so? Now, if you want to use an existing method, again, you'll have to provide an exemplar. And this exemplar is going to need to be large enough to convey the coarsest features of your texture, and also have enough resolution to resolve the finest features. And for this particular example here, this is going to require an image, an exemplar image, on the scale of almost gigapixels. So clearly this isn't going to be easy to work with, either from an authoring or from a computational standpoint. And actually, even if we did have enough patience and computational power to synthesize an image such as this one, it still wouldn't solve all our problems. And to illustrate this, I'll show you another texture. And this time we have a gray background with black and white spots of differing scales. And in fact, if we zoom in a bit, we see in fact that these spots exist at all scales. Or in other words, this is an infinite scale, infinite resolution texture. So if you're familiar with texture generation, you're probably thinking, well, this is a situation where we need to write a procedural texture, because to put it simply, there's no such thing as an infinite resolution exemplar. And this really gets to the root of the problem that we have here, which is that a single finite exemplar is just not going to be able to express the kinds of multi-scale textures that we're interested in. So before we can even start talking about multiscale texture synthesis, we're going to need a better way to describe the textures that we want to synthesize. So we need a better input representation. So now I'll describe the input representation that we've come up with, called the exemplar graph. Formally speaking, this is a set of nodes and a set of directed weighted edges, but there is a more intuitive explanation. So let's get into this example. This is the graph that describes that map-like texture that we just saw. And the nodes of the graph are exemplars. And we have different exemplars to describe each of the features that we want to see in our texture. So we have a coarse level exemplar that describes the overall distribution of land and water, maybe an exemplar for island chains, an exemplar to show what a mountain range looks like, and so on. And the thing to notice here is that all of these images are the same size. They're small exemplars, about 256 squared. But they all show features at different physical sizes. So what we've done here is to decouple the notions of physical scale and image resolution. So we're going to need some way to recover those relationships, and that's what the graph edges are for. As an example, let's take this edge here. It points from exemplar A to exemplar B, and this tells us that the features in B are also present in exemplar A. The graph edge, the edge weight, in this case 3, tells us the scale relationship in between the exemplars. So it tells us that pixels in B have been upsampled 3 times in relation to when they appeared in exemplar A. And that's pretty much it. It's a simple definition for the graph, but you'll notice that we've placed no restrictions so far on the connectivity of the graph. And in particular, we allow for loops. And to see the implications of this, let's go back to this infinite texture. And this is the exemplar graph that we used to describe and to synthesize this. It's a single exemplar with a single self-pointing edge. And the edge weight of 1 tells us that this texture is similar to itself when scaled by half. Or in other words, we've recursively defined this infinite resolution texture. So we see that the exemplar graph is a simple but powerful and expressive way of describing textures, and more to the point, multiscale textures. So we'll be using these as the input representation for our multiscale algorithm, which I'll describe next. So as I mentioned before, example-based synthesis has been around for quite some time, and a lot of the ideas from existing methods can be reapplied in the multiscale setting, and this is fortunate. So hierarchical methods work by building an image from coarse resolutions and gradually refining to finer ones. And this is going to suit us well because we particularly care about the content of each frequency band. Non-parametric methods avoid building statistical models and instead copy data directly from the exemplars. And again, this will be useful for us because we care about preserving features. And finally, there's been recent work in parallel methods which allow us to do things like generating deterministic windows of texture and also to even perform synthesis in real time, in some cases, on the GPU. Now, in particular, we'll be adapting and adding on to the algorithm by Lefebvre and Hoppe, which adopts all of these ideas. So this is a hierarchical method. So we start from a coarse resolution version of our texture, and we gradually refine and add detail in a series of passes till we arrive at the resolution that we want. And this results in a series of images that collectively we'll refer to as the synthesis pyramid. Now, by construction, each level of the pyramid is at twice the resolution, or half the physical scale, of the next coarser level. And this is going to be a useful fact for us in a moment, so just hang on to that thought. And also, as with other hierarchical methods, we begin by pre-filtering our exemplars at a series of coarser resolutions. And we're going to perform this as a preprocess and store the results in a structure that we call the Gaussian stack. And again, the Gaussian stack levels obey this power of two relationship where each level is at twice the resolution of the one before it, of the next coarser one. And it turns out this is going to be very useful for us when dealing with the scale relationships in our exemplar graph. As an example, let's take this simple graph. It has two exemplars, and let's look at their associated Gaussian stacks. Now, the edge weight tells us that they're related by 3 downsamplings. And schematically, we can represent this by offsetting the stacks by 3 levels. Now, notice that when we draw the stacks this way, levels in adjacent stacks have equal scale. And this concept applies to more general graphs. So looking at the pixel scales of these 3 Gaussian stacks, we notice that the same relationships were seen also in the synthesis pyramid. And this is going to be a very useful and fortunate fact for us, because it tells us that at a given level of synthesis, we know exactly which pixels from the Gaussian stacks to use, namely those having the same physical scale. Now, Lefebvre and Hoppe also noticed this, and they introduced coordinate synthesis, which we'll also be using. And here, instead of storing the RGB colors in the synthesis pyramid, we'll actually be storing pointers into these Gaussian stack levels. And since we have multiple exemplars to consider, we have to do a little extra bookkeeping. So in addition to just UV coordinates of texels, we also store an index that tells us which stack we're looking into. And at any time, we can recover our rendered image simply by dereferencing or looking up these pointers. And so for the rest of the talk, I'll be using this rendered image representation of synthesis levels, but just keep in mind that under the hood, we're keeping coordinates. So then, how do we actually build this synthesis pyramid? As I mentioned, we do this in a series of passes. And in each pass, we perform 3 intermediate steps to get to the next level. First, we upsample the previous output to get an image at double the resolution. We jitter to add some amount of visual noise to the texture. And finally, we perform a step of correction, which brings us back to the appearance that's prescribed in our input. So let's get into detail on these. The goal of the upsampling step is to create an output, outlined here in red, that matches the appearance of our input, outlined in blue, except at twice the resolution. Or equivalently, for each pixel in the input, we want to produce a 2x2 patch in the output that matches the appearance. And since we're working with coordinates, this turns out to be fairly easy. We know the coordinate for any given pixel in the input, And we also happen to know where to find a 2x2 patch that matches this texel, namely in the next finer stack level at the same location. So we simply copy these locations over into the 2x2 patch of into the finer output. Next, we jitter the image, and this is to add some visual variety to the texture. And again, since we're working with coordinates, this is going to be easy. We just add an offset to each coordinate that's stored. And we get these offsets from a hash table that we fill ahead of time with random values, and we actually hash pixel coordinates into this table. Now, jitter it's useful because it adds visual noise, but it's also kind of bad for the same reason, because now our image does not resemble the exemplar since we've added noise to it. So this last step of correction, the aim is to fix that. Now, intuitively, we want every neighborhood locally in our output to resemble some neighborhood from the input, from the exemplars. So we're going to collect at each pixel the 5x5 neighborhood around it, and we want to find the best matching neighborhood from some level in our Gaussian stacks, and specifically those having the appropriate physical scale for our current level. Now, once we've found this best matching neighborhood, we simply store its coordinates back into our pixel of interest. Now, we're also doing this in parallel for all of the pixels in our synthesized level, so we're also going to have to perform several iterations of this process to get to converge to a nice solution. And those are really the basics of our algorithm. So you've probably noticed, if you're familiar with texture synthesis, that this resembles a lot of previous work, and we consider this a very fortunate fact. It means that with just a few simple modifications and understanding and a little extra code, you can start generating multiscale textures from your existing code base. But there is a catch. There's always a catch. And in our case, it's that exemplar graphs can be, in some sense, wrong. So as an example, I have this graph here, which at coarse levels, it prescribes a rainbow striped texture, but at finer levels, we've prescribed this blobby black and white appearance. And this is a situation that we call inconsistency. And to illustrate really where the problem is, well, this is the image as we go through synthesis at coarser levels. And so far, this looks like what you'd expect. It resembles the appearance that we've prescribed in the exemplar, in the coarse exemplar. But now we reach a point where we need to start using texels from the finer blobby, or for the black and white exemplar. And so if you try to color a color image using black and white pixels, you're not going to get something that resembles anything you've done before. So this is not the result that we want. So we want something more like this, where we have at coarse resolutions the coarse appearance that we prescribed in the graph, and also preserving the finer features that are in the finer exemplar. This brings up an important precondition that we place in our synthesis, which is that the coarser levels of the synthesis should act as a prior for the finer levels. So to enforce this, we introduce a procedure called inconsistency correction. So you'll recall that during the correction step, we took neighborhoods from our synthesis pyramid. We found best matching neighborhoods in our Gaussian stacks. Now, in situations where you have inconsistent input, even your best match can turn out to be fairly poor in an absolute sense. So we also additionally, for each of these neighborhood and match pairs, fit a transfer function. And the goal of this function is to recolor the best match so that it resembles our original neighborhood as closely as possible. Now, once we fit these functions, we store them back into the synthesis pyramid along with those coordinates. So each pixel in our synthesis pyramid also stores a transfer function. Now, I've done a lot of hand waving here, and I've left out a lot of details of the algorithm, so before you go implementing, I would strongly urge you to read the paper. But at this point, we're just going to get into results. So we'll start with a simple graph. And the point here is to show the efficiency of our method. So we have a simple exemplar graph with just 4 exemplars. They're very small, I think 128 squared. And they generate this rusted metal texture that's on the order of about 8K by 8K. So our savings is on the order of about a little over an order of magnitude. Here we have more of these recursively defined infinite textures. This first exemplar we went to the park and took a photo of some rocks. And we used it to define this infinite texture that's rocks made of more rocks. And you'll notice we have these coherent, consistent zooms into this infinite texture. Now, this is an example of a captured exemplar, and so the next one will be similar, but it's artist created. And next we have a graph that we sort of threw together in a few minutes to see just how easy it would be to create an exemplar graph. That makes sense. And you'll see that each of these exemplars prescribes the appearance of the texture at a given level. And so again, this is the sort of thing where to do it procedurally it would take a long time and be pretty hard, but just sitting down in Photoshop, we were able to do this in a few minutes. And you'll notice that also the exemplars are themselves fairly inconsistent. So we relied on inconsistency correction to fix that situation. Now, another interesting application is a form of super resolution. So you see here a graph made of images we pulled from Google Maps. And at the coarsest levels of synthesis, we turn off jitter. So this constrains the image to match the coarse exemplar, which in this case is a map of Japan. So as you see zooming around, all these details are being filled in just through texture synthesis. So now I'll close with some future directions that we see for this research. And the first is in the area of designing exemplar graphs. A lot of the graphs you've seen so far have been arrived at through careful iteration on the part of graduate students and professors. But ideally, we'd like artists to be able to eventually create these graphs. So one area we see that could be really important is real-time preview tools, where you can, in real time, modify your exemplar graphs and also preview their outputs. And also, we'd like another interesting avenue is an automated creation of exemplar graphs just from large images. And in a few talks, you'll see a paper, inverse texture synthesis, that we think can apply in the multiscale setting as well. And also, so far we've only been looking at a fairly narrow window. We've been looking at graphs of RGB textures and using a specific synthesis algorithm, but we think we can extend this in other ways. Specifically, there have been optimization-based, example-based texture synthesis frameworks, and we want to see these applied in a multiscale way. And also, we think there are applications in synthesis on large surfaces. And finally, we'd like to look at higher dimensional data, like appearance space or normal maps, things of that sort. And so with that, I'd like to thank you for attending this talk, and I'm happy to take any questions.
Okay, let me ask a question first. So in your future direction, you mentioned automated generation of this exemplar graph. Mm-hmm. Do you actually have any thoughts on that? Even it's very initial thoughts.
In terms of code written down?
No, not code. See, how roughly would you proceed in that direction?
I think the best analog to that paper would...
suppose given a large collection of images, manually doing it would
right.
be,
Well, we were thinking more like just a very large image.
Yeah.
So in the inverse texture synthesis paper, they fixed the size of the output. They say we want an exemplar this large. So we think the analog would be to specify the total number of exemplars you want in your graph and constrain it that way. And then from there, I think you can start going again in a coarse-defined manner.
Mm-hmm. So do you have thoughts how to define these links between the different texture examples?
Well, that's sort of the trick. That would be kind of the contribution of that paper, I believe.
Mm-hmm. Okay. So I think this kind of work would be very useful for zooming like Google Earth, right, from space until you see the grains of the surface, terrain surface. Do you imagine some other scenarios that this can be useful?
As I mentioned, we have the super resolution kind of example where, again, if we were able to analyze these multiscale textures better, I think we could have situations where you just say, this surface is metal, can you please add some detail to it? Mm-hmm. Things like that.
Okay.
And also, there's lots of situations in movies where you have large textures, and
Okay.
you may want to perform some large zooming thing, and you don't want an artist to sit there and manually match up the textures at each scale.
Now we have a few minutes for further questions. Feel free to come forward to the mic. Yeah.
Yeah.
Please identify yourself.
Yeah. Jean-Sébastien Gay from CM Labs Simulations. You mentioned possibility of implementation onto the GPU or for real-time texture synthesis. Have you done any work in that direction, or your current examples were pre-calculated movies? I assume.
Yes, they were, and my apologies to Eric, who's sitting in the front row, but he did implement our algorithm on the GPU.
Okay.
The details are in the paper. We do have to perform some crunching of the data ahead of time, which kind of prevents us from doing the largest graphs, like that Japan graph. But we think we've also actually been looking at kind of ways of more efficiently crunching that down, so we can do it on the GPU. Also, the full algorithm I have implemented separately on the GPU, but not in real time. So just using it as a huge parallel processor.
So I guess it'd be good for kind of virtual texture compression, kind of using a few exemplars to synthesize a much larger texture.
Yes.
Is that possible in real time? I mean, are the savings actually going to compare to what you would have gotten from a larger texture? You mentioned some pre-computation.
Yes.
How much space does that pre-computation take? Sorry.
Yeah, as long as you have the space, as long as you have the algorithm to synthesize, the space savings are there. Just in terms of the graph lets you save, powers of 2 in terms of over previous algorithms.
Okay. Thank you.
Hi, Mark Cooper, DreamWorks Animation. One of the things that you're sort of advocating here is abandoning very large textures for this more procedural approach. Do you have any sense of the time trade-off? What are the trade-offs what are you giving up versus what you're gaining? One of the things that we encounter a lot in feature work is we're covering very large areas, and sometimes the camera is right here and sometimes it pulls way back.
Right.
And we're always going through that trade-off of, do we generate this whole thing procedurally and sort of let it run every time, or do we just generate a large frame and have it done? So what kind of time trade-offs are we looking at?
Well, the time trade-off is you only synthesize exactly the scale that you need and none of the finer ones. That's what we're advocating. The trade-off is actually in quality, where at the finest levels, if you follow a traditional approach, you'll have a lot of fine scale detail in that humongous texture that you're putting out. And in our case, we try to represent that using a few fine level exemplars. So the savings are the best when that large texture is very repetitive, and that single fine level exemplar can actually capture all these otherwise redundant pieces of data. In terms of speed, we gain everything by going to a multiscale approach, since we're using less data and we have less to consider.
Thank you.
Any other questions? Okay. Let's thank the speaker again.